I think we can start now, or should I wait a bit longer? We can start. Okay, so the first task that I'd like to discuss, I've given it to you in the Discord. So please try to think about it for now. In the meantime, uh, I'd like to show you a little something. Maybe you like it, maybe not, but it's the implementation I've been taught to use whenever it comes to talk about segment trees. And I think in general, they show a paradigm of programming that is quite useful when it comes to uh, keeping code as shortened as universally applicable to more problems. So, if anyone wants to discuss any ideas, you can do so in the either on the document or on the meet to comments. Um, okay, so today I'll focus more on Sweetline, although maybe that's a bit sensitive to think about. Generally, Sweetline is defined as whenever you need to, I think, at least that's my opinion, to keep a segment tree that is updated every time you uh, traverse either an array or a matrix or so on. So it keeps information for each position with regards to something in general. And I think the problem I've given you is quite clear, at least in the most generic stripline terms, because you have a time axis and a location axis. So maybe naturally one might think to represent whatever operations happen here in a 2D plane uh, with time as the OI axis and the position as the OX axis. And you might notice that queries they give you are some shape in the 2D plane, and something should happen that we uh, solve the problem basically to get those queries, whether they are like figure some queries or range maximum queries or so on. So yeah, that's what I think sweetline means. But before all of that, uh, uh, I just want to flex, I think. So I'll type right here a segment tree template that I think you might have noticed, I think, in day two when actually in my implementation for the task extra swap. I'll discuss it in more detail here, and I hope that you'll come to appreciate it and maybe use it in the future. So, first of all, this line, I'll explain it. Basically, it means that I have encountered this, whether you've actually used it or sometimes it appears as errors in the compile, especially when you do something like maximum from int and long long. It's basically tells the following struct that it may take uh, something that is constant throughout the code, and especially in our case, it will be a type name that is another struct or class that we can that a struct that follows can just black box and assume that is completely valid. Uh, this is to say that maybe you'd want to use both int and long long, for example, but you don't want to implement a segment tree for ints and a segment tree for long longs. and you can just send as parameter the type name in such a case. Well, in our case, it won't be int or long, but some complicated struct that can pull information and push information. Okay. Then, in such a case, we can uh, define our segment tree. Obviously, it's there are only two parameters for a segment tree. That is the information that it holds and the maximum number, the number of elements in it. And to initialize, we can do the following thing. Uh, Maybe some of you, I'm not sure, are familiar with the four times n paradigm. That is, you need to assign to the memory of the segment tree at least four times the maximum number of elements, just to be sure that you're not past the that you're past the correct power of two or whatever. But I will show you a very simple trick to make it two times n, and by those means also essentially a bit faster. Obviously, this means that please create uh, segment tree that has two times n plus five elements, and in each of them it places the empty type name. Then instead of implementing update query and whatever, I will implement just one function, which will actually be three, but that's just for convenience. Okay, so what have I done here? And this is a little foreshadowing because I can't actually get into details until I fully implement this real function. So um, you might already know, and very well so, that segment trees work because we can split any segment into a total of log n segments that are already represented. Uh, what's the problem statement? There is no problem statement. I'm just showing you my implementation of segment trees right now. Uh, in the meantime, if you are bored or whatever, please solve this task. It's on the Discord. I'll pin it, I guess. I hope everyone can see it. So it's problem festival from Kilonova 3720 on VJudge. I can't actually zoom this. Okay. So as I've initially said, this means that I'll send as parameter something that doesn't really uh, regard me, but I know that uh, basically this means it's a not a data structure, but type name. I'm not actually sure. I'm not a good programmer. What the difference between a type name and struct is? I think type name includes things like int or it was something about the static cast, but I don't care. Uh, but you might notice that I also use it here. What I intend to do is instead of implementing an update function and a query function, to implement a single function that will later be able to perform all the tasks of any possible function ever. And you'll see what I mean by that in a minute. Why is that? It's because generally when you have a simple segment tree with like maybe sum and range query, okay, that's fine. But in any hardware problem, you might encounter that you need to do both sum um, uh, sum or then maximum on some other thing because you only actually need to access one single element, then update on range, then binary search first position in the segment research that la la la. And there are a lot of functions. but every single time you are forced to copy the entire template of DFSing the actual segment. It takes like 80% of the logic that one would actually have to write in uh, in a single uh, uh, such function of getting the sum, updating, and so on. For instance, I can show you what at one point used to be my segment tree template, which I'm not sure how. It has like, yeah, 150 lines. And look, like I have set on position P some value. And like I have to do all of these irritating things just so that I can essentially just set the value here. Like this, like the entire function could have been just this line, but instead I have to write all of this stuff, which you might notice I'm also writing again here. And then in the query again here, I could have just written this line, but instead, look, I'm writing everything. Uh, Not to mention find uh, this entire find right thing, which is a bit awkward. Uh, and yeah, like a lot of code repeats itself, and it if you were to debug it, it looks like very bad to try to find a bug when essentially the actual logic or where your update or like binary search function should fail is condensed into exactly two lines, but you have to search the bug throughout like instead of only two, but like 10 of those lines, which is bad. Uh, so let's just try to write the most generic DFS on segment tree thing that we can. And knowing that also we really want to access only the information from some segment. You later see that this implementation can also adapt to like segment tree beats operations very easily. So, uh, okay, uh, if the current segment of the segment tree that we are in is out of bounds and irrelevant, then just return. There's no point. Otherwise, if it is fully contained and something happens, which I'll describe later, also return. Then we can now write the segment tree logic by itself. I'll explain this in a moment. Oh no, I should I? Okay, so what happened here, and this is another trick that's irrespective of the rest of the code, um, is that instead of doing the classic node as its left son as 2 times node and its right son as 2 times node plus 1, I instead initialize them with these weird values. But essentially, what they are is what the pre-order on the DFS is, with the pre-order of the DFS on the segment tree would look like. Because if we are currently at node, then we are going to the next node that we'll visit will be the left one. So by pre-order, it means that it will be plus one. And with regards to the pre-order, the right node will appear only after we've encountered the entire subtree of the left node. And we know that the size of the left subtree is this. It's the length of the segment it represents times 2. So the right node can just get that pre-order. We can calculate its pre-order. This is much faster because, and this is recommended to other problems where you have to squeeze in a lot of DFSs, maybe like n squared, well, no, O of n DFSs of O of n time each, is that if you were in the memory to jump like this from node to 2 times node, and like in the memory you jump to random positions left and right, then there is a lot of uh, uh, like time that you need to take in order to actually access those points in memory. Because accessing points in memory is not really O of one. I mean, it is O of one, but it has uh, time complexity. I mean, we assume it's O of one in the RAM model, but it actually takes some physical time in the computer. Especially if you jump left, right, left, right, left, right, you need to have a little like pointer that goes in that place of the memory and actually read it. And because generally it assumes that you do not do those sorts of jumps and you work with local memory a lot of times. When you jump from one position to the other and it sees that it's a completely new position, it tries to put all the elements around that position in what is called a cache, which is memory which you can access like instantly, except with like this overhead that I keep mentioning. So then, because you also have to load all of those elements in the cache, although you only want like one specific thing in that memory, it also takes more time. And so it is generally uh, recommended that the positions in memory you access sequentially are consecutive in memory in the list of the memory. So in such a case, because the left node will be the immediately next node that we will access, and because it's stored in the memory next to the node that we are currently accessing, then accessing it will be free with regards to the operating system. Okay, good. What means end? Well, where? You mean here? What does this mean? I'll get to it. Like I will get to it exactly now. Um, okay. So I kept running my mouth about how we're supposed to DFS on the segment tree and like use the logic of the code actually later and not in every single function. So how do you implement the logic of the code? Well, um, we can, and this is what I've done so far, is send a function through the DFS that when it needs to be called, and that is generally when we are in a desired segment that is completely included in the segment that we are searching, um, we call it. So we are going to call it with the information that we have in the current node and what the current segment. This is a thing I like to do because sometimes it is useful to do so. To also send what segment you are, the information is responding to. Because function does not know anything. What? Oh yeah. Yeah. That's another thing. I'm not a good programmer. I don't know. Um, like I remember very briefly. So normally one single thing is sent by reference, and you'll see that this is a lambda. And someone explained to me once why sending by reference lambdas is bad, but I forgot. But this, what it means, if I remember, is that you are sending by reference a right value. So there are, I think, I really hope I'm not mistaken. Um, actually, let me check. What does mean? Okay, yeah. Whoa, I'm so smart. Okay, so what this means in this case is that in C++, there are two distinctions of values. There is of objects. There are L values and R values. And what they mean is that an L value can sit at the left of such an operation. Like you can assign things to the L value, whereas the R value you cannot uh, assign it values. For instance, if we were to write int n see the following program, then you'll get an error which says, okay, you won't get an error because my computer is slow. Okay, L value required as leftover and of assignment. So uh, 6 is not an L value. You cannot assign things to constants, essentially. So in such a case, what we do so is we want you to transmit the reference of this function that I'm giving you. But additionally to that, note that at no point in time will I ever assign things to this function or assume that this function will change throughout the course of this. It's not supposed to be considered as a null value, and you cannot assign things to it. But in any case, please refer to the exact position in memory which I've given you the um, object in. So when I will do this, something like this, it will call exactly this function that I've initialized here, but it will never change it, which is a bit faster because it doesn't have to assume that maybe this will change at any point. So it knows to treat it almost like a constant, and I think you might also be able to set it as a constant. Uh, Although I'm not sure how that could change really, what the difference between this is and this. But yeah, this is very vague. But I type it every time, so it never failed me, and maybe it will never fail you as well. Don't know if that's satisfactory. I don't think it will be. Uh, but did you black box in it? No. It's initialize initializing a segment tree is just like setting the things in the memory, and that's it. We may have another function of initialization, like if you want to initialize with all the elements from some array, and I'll show you very soon how to do that. Okay, so back where we were, this is the entire logic of the segment tree. This is where the entire logic compresses. We will call a separate function that tells us not only how to change the memory in our segment tree, so maybe this function will change the memory in the segment tree because we'll pass this by reference, but also, and this is very important, whether we actually want to continue DFSing. Because, for example, as I previously hinted, if we want to assign to all the leaves the values from some vector, so we have a vector, we read like vector, and we want to assign V to every leaf in second. Uh, yes, isn't it better to use? Uh, I don't care really. Maybe not. Uh, I think you can in such a case. I'm not the but like I've always implemented it like this, and then I saw this implementation, and I wouldn't know to make a recommendation for either, whatever you are most comfortable with. I do admit that this is a bit goofy, having to add plus one every single time, and that might be irritating for some, which is why I'll while half open might be good better, but uh, I've never read any literature or whatever stating that one is mathematically better than the other. I personally dislike this because it's a bit irritating for me to think, oh, I need to query from the sixth position to the 13th position. Let me call sec3 query from 6 to 14 because it can't actually aggregate the information until 13. Like I want to be able to query other from L to R, and yeah, but you can use either. It won't change that much. I think just this disappears and disappears instead. Yeah, that would be a modification to have it half open. Uh, but I'm not a particular fan of that. Okay, good. So this is a lot of talk, but if I'm not actually showing you how you can do this, it's useless. Um, so first we need to initialize a type name. Um, let's say we want to do range sum uh, point update or something. So in such a segment tree, all the information that we need is just the sum of the current segment. We should build a constructor also, and we do so. We initialize it with zero if there are no other past parameters for the constructor, which is essentially useful because here I've assumed that the default constructor for any object of type name t will be the identity element. That is the thing that you can keep adding to itself without actually changing any of the information. And so zero is an identity element to summation because 0 plus x equals x. Then we need to implement these two functions. Well, two functions need to be implemented. We can implement much more, but whatever. Um, we need to pull information from the left side and the right side, and that's pretty easy to do. And also we need to push information, but in case of lazy updates, but won't be the case currently. And so let's build such a segment. Uh, so as I've said, let's build a segment tree where we've read the initial elements of the segment tree, and now we want to initialize it with those values. So what should we do? We should call the only function that we have. Oh, well, we actually have two functions that we need to call both. Sorry. So need to initialize the segment tree and tell it that it should have so many nodes in the memory and whatever. And now we should walk the segment tree. No. And in every single function, you've noticed that I'm passing this parameter, which is called CB. It stands for callback because you will call back a function from way back that will tell you what to exactly do. So because this function seemingly returns a bool, and we can tell it that it does return a bool like this, but this is useless because it deduces this information. Uh, and it could be an int, we don't care. We notice that it says if it returns false, then return, but if it returns true, then continue DFS, even if you are already completely in the segment. And because we want to set to each leaf, we want to get to each leaf. And we don't care that, I mean, we have to iterate through all the segments that are included in one end, but we only actually want to get in the leaves. So if uh, the left endpoint is different from the right endpoint, then we return one. I say return one. This is purely a convention that I came up with because it sort of says like if I return one, then you need to continue. Otherwise, if I don't return one, then you need to stop. Otherwise, CL equals CR. And so in such a case, we're in a leaf node and we know the position where we correspond to. So we can just set the current value to be equal to the corresponding value in the segment. And then we need to iterate through all the elements. So yeah, send the segment. Although by default, if you don't send the segment, it will be considered to be the entire array. And now let's do some queries. And let's say one is update. Then it would look like this. Uh, no, I can actually do this. Okay, so what have I done here is I've sent a function. Oh my god. Yeah. I sent a function for update, which looks like this. So it calls this function. It tells it that the sought interval should be the one from L to L, which is basically the leaf. And then, so then when we get to the leaf, um, we tell the leaf that its value will be that of the value that we want to update it to. And if you want to do a summation, then for all the segments that are completely included in LR, but essentially those that are maximum with that property, we add their sum. So basically, the first time that we get here in a segment that is completely included in LR, we call back with the information from the segment tree. It goes here. We add it to our value, and then we return. So let's test the code. 10. Oh no. Oh no, never mind. Good. So let's query from the second position to the fifth position. We get 11, which is 6 plus 4 plus 1. That's correct. 2 from 7 to 9. We get 8, which is plus 4 plus 2. Correct. Let's update position 8. 100. Now we will query from 5 to 10. Get 123. So the sum of this, 9 plus 2, 11, 15. What? Wait. Oh no, this is positioning. So 11 plus 10 plus 2, 23, plus the 100 that we updated, 123. And yeah, that's it. What I additionally recommend is that you build an inheritance class above uh, such a class. You might, so why this is useful is because in some problems you maybe have to have a segment tree for maximum that is updated somehow and another segment tree for some that is updated some different way, and you'd want them to be different. You don't want the thing with a maximum to be in the same place as the thing with a sum. So this is why this is useful, because now you can write something like this. Or and the segment tree, because we built it as an inheritance class, it still functions as a normal segment tree, but we can build like these smaller things on top of it to keep our code clean, because this is actually ugly. It's ugly to write code like this. Because I don't need to see the logic here, because I need to ideally black box it. Now I can just write It isn't. Why? Why isn't it? Oh, yeah. So you may see that it gives the same results as before, and it works just like before, basically. We can also have like void init from array vector into v, and we can do this. Okay, I don't care. Oh yeah, so that's it. Uh, are there any questions? As I've said, technically you can implement binary search on segment tree and the segment tree bits thing under this same structure, and it follows very nicely because it's just a matter of implementing one more of these queries. Does anyone want me to see me writing a binary search, for example? Yeah, like case element or something. Well, in this case, because we have some segment tree, like uh, for a given position L, tell me mean R such that some L R is greater than K or something. Uh, what if K is from I index? So for a given L and K, give me the minimum R such that the sum from L to R is at least K. Sorry. So this. Let's see. Okay. So we will only use the walk function. So let's search int L int K. I I want to say that technically I'm setting all the values to int, but they should be long only, not real problem probably. So we will walk function, which we will implement, but more importantly, the range of all the segments that we need to cover should be from L to N. And let's see, say that R will be equal to L minus 1, because this is the hypothesis that, okay, so we want actually max R such that some L R is less than K. So we will say that this is equivalent to calculating this. Because if we calculate the max R such that the sum is under, then the next R will be the minimum R such that the sum is over. And this R clearly holds. Well, if K is 0, then it doesn't, but we don't care about such cases. This R clearly holds. So we know if um, R plus 1 is less than CL, then what does this mean is that the last candidate for R that we've found uh, is not yet in the segment, is like way before this segment. So what this means is that we iterated through a lot of segments during the DFS in the segment tree, and it's very likely that we've already found our candidate. So then the new segment that we are trying inadvertently because we are DFSing on the segment tree is like so much further that it doesn't matter because we already found our solution. So basically, if we've already found our solution, we don't care. Also, this will never happen, but I try to be cautious. Uh, yeah, this is meaningless, I think. Okay, good. Then, and I hope this is it. If the sum from the node is less than k, no, strictly less than k, then the r could be the right endpoint of the segment, but we've already exhausted this sum. So furthermore, when we search further right, we need to like delete it or whatever. And we are done with the entire segment. The solution won't be in this segment anymore because it's the right endpoint. Uh, worst case. Well, yeah, worst case is the right endpoint. Otherwise, it might be even further right to the right endpoint of the current thing. Otherwise, if we are in a leaf node and we cannot include the current segment to now it should no, now it doesn't. Oh, it works. Okay. It works now. No, like I see my circle flickering, so I assume it does. Um. Okay. So let's start at position number 3, and we want the first position when the sum is at least 16. Uh, 3, so 316. It says 6. So this is 3. Then 3, 3 to 4 is 5. 3 to 5 is 7. 3 to 6 is 7 plus 7, 14 plus 1, 15. 3 to, yeah, 3 to 7 is 17. Okay, so I forgot to add plus 1 here, maybe. Doesn't actually matter. Now, instead of calculating what I initially said, I want to be the minimum R such that the sum is greater than K. It actually calculated what I said to be the maximum R such that the sum is under K. Because you can see that from 3 to 6, the sum is 15, which is clearly less than 16. Additionally, if I do this, it will output 5 because the sum from 3 to 6 will be exactly 15. And I want the first the maximum sum such that is strictly less than 15. So strictly less than 15, it means that it has to end one position before. So yeah, this is basically the logic of what a binary search would look like. and you can just implement it here. Or like I mentioned this for those that know, uh, but the code won't be valid for given structure. I have to implement much more, and I'm lazy. I'll share one of my implementations with you. Actually, I think I might be able to find it right now. Uh, yeah, I think this is it. Um, okay, I was much younger then. Um, so this is what an update for segment 3 bits would look like. So you have the node, left value, right value, and the range that you want to apply the operation to. And maybe some of you know it looks like this. So if currently the minimum is this is for change max 0. So if the current minimum is greater than 0, then you don't need to change max anything because if even the minimum is above 0, then it's fine. Then if only the minimum is below, no, if both the minimum and the second minimum are below 0, then you need to go further down. Otherwise, only the minimum is within the uh, yeah, only the minimum is below 0. So then you only change the minimum, and that's it. This is what the much hated segmented bits looks like. At least the DFS for it, because obviously you have to also write this entire stuff, which is not so pretty, but yeah, yeah, that's a lot of lines for a single operation, but whatever. Uh, so, are there any further questions with regards to this? I will send it to you in right now. And I recommend that you use it. Okay. Uh, okay, so this was a lot of time. Unfortunately, I wasted a lot of time on this. So now I will jump right into this problem. First task I sort of forgot, but whatever. Okay. So are there any ideas for this problem? Any ideas? You might have ideas in n times log squared, but I will show you a solution in n times log. Yes, invincible. You raised your hand. Whatever. Yes. Does DP work? Clearly, yes. DP does work. Uh, but yeah, currently we have like do list with transition, like list. What does list mean? List means that if ij is valid transition, then dp of j equals x dp of I plus uh, or dp of j, something like that, and dp of j plus equals sj in our case. Uh, and the transitions are valid in such a case. But the issue is that obviously, naively speaking, there are n squared candidates, which is bad. It's bad because if we do not reduce the number of candidates that we can choose from, on which we will apply this transition, then we can't optimize further than O n squared. And it turns out that we can't actually reduce the candidates per se, uh, but there is another thing that we can do. So, for example, if the transition was valid if Tj was greater than Ti and Ti was greater than Tj minus some k, Kj, then after sorting by T, the all the valid transitions would be in a segment. So that means that if we sort by, if this were the problem, if this is what the problem told us, that the transition is valid if this happens, and then we sort the events by T. And these would be the elements. Then for this particular event, the condition would tell us that we are supposed to take the maximum of dp of I, where I will be on some range like this. So then we know we can apply something like a segment tree for this specific range. Uh, do you agree with this? Because I'm not sure if I was clear. So is it clear why this particular problem, like if instead of having all of these conditions, we only have these two conditions, then the problem could be solved with a segment tree. Are there any questions regarding that? Or did so okay, I hope yes it is clear, because if there are questions, you may write them. Okay, so we should strive to find such a representation because this is very useful. If it is on a segment, we can do segment tree. We should find such a representation of whatever this means, whatever these conditions imply. But in such a case, we not only have one single parameter that tells us whether I is a valid transition, but we have two. We have a function over t and a function over x, and also a function over t and x, which is a bit irritating. Um, so what I suggest you do in many such cases is to try to draw what the region, because this will essentially be a region. It won't be a bunch of random points. Uh, what this region is in the 2D plane. So this is position or x, and this will be time, I think. So T. And let's look for a fixed Tj and Xj. What the ranges, what shape on the 2D plane will look like of any xi that is valid under this parameter. So let's say it is right here. Then this condition tells us that we need to uh, take any. So the first two conditions tell us that first of all, it needs to be under t. So in this half plane, then this condition tells us no, that the further candidate should be in such a rectangular region. And also, this tells us, frankly put, that uh, for a TJ, a TI over here, we should take the distance. Okay, so the distance on the time should be greater than the distance on the uh, yeah. So the uh, OY distance from this point to this point should be less than the OX distance from this point to this point. So then, what would happen actually if this was equal sign instead? Then it would mean that both the OY distance to this point and the OX distance to this point is equal, and in either direction. So then that would mean that this is the range of points where Tj minus Ti equals Xj minus Xi. And because we want actually for this to be greater or equal, it means that the sought region that we want is within this cone. It's within this cone. So by the end, what we will have is the following region of all the valid points. So it looks like a little house, I like to imagine. So again, for clarity, uh, xjtj over here can take its dp from such a region. Okay, good. This is well, this is not good because it's maybe hard to solve, but it is good. So if we had like a magical segmentary that we could query for what is the maximum value on such a planar region, pencil house, whatever, then we could go in increasing order of TJs, for example. Then we'd get the query for this entire subregion, and then that would be dp of j. We'd get the maximum from the entire region, and then we'd add like sj, and we continue so on and so forth, and then we take maximum dp. Is it sort of clear? except for the fact that we have to do this query. We don't know how to do this query. But if we were able to do it, uh, is it clear? Why house shape? Uh, because because of the three restrictions. So first restriction tells us that it has to be below. Okay, it is below, and all the restrictions are like with and. So we need and between them. Then, oh my god. Then the third restriction tells us that it needs to be within like this region, like at at most uh, the points away from the point on the left side and the points on the right. Although we don't actually care of the things above because, as we said, the it needs to be lower. And then the third restriction basically adds this rooftop because it tells us that everything within such a cone is acceptable. So this entire thing is acceptable. But because we have to take the end of all of these, we'll have like for a while we'll be bounded only by the second restriction. So we only need to be within the cone, but then the cone gets too big and we actually only need to go downward. So I hope it's clearer now, although it seems like even before that it was clear why we need a house shape. So initially I said that we need to sort by T chain. Okay, let's actually return to uh, and also initially I said that uh, we should sort by TJ and query this region. Maybe some of you already know what sweepline is, but sweepline is the notion that, especially in such 2D cases, you'd have a data structure, normally a segment tree, and you'd aggregate information as you go line by line. So at first, it has all the information that you need for this particular line, and then you go one line above, and then there are maybe some updates, and then you do those updates, and you are able to do those updates, and then the segment tree still has all the information for this new line. So, namely, if instead of a house shape, we would have like a box shape, which is still very hard to do if it's a random box, but let's assume that it's a box like this that has its lower base equal to the OX axis. Because if it's a random floating box, then it's not unsolvable but hard. Then, what we could do is we could keep a segment tree, or which for each line at any point in time initially just holds for this column in particular, what is the maximum value from on this column until the very bottom. Then when we go one line above, there are maybe some new DPs that appear. So we need for this position to uh, update the maximum in the segment tree. So sec3 of I, change max with new DP of I, for example. And then when we need to do a query on this sort of range, on such a rectangular range, because each position holds the maximum for its entire column, then we can take the maximum on a range of columns. And then because we take the maximum on the range of some columns, we actually get to describe the entire submatrix. Is that clear? This is like a standard paradigm. Okay. And I'm still beating around the bush without saying how we should calculate the house. Obviously, if we were to keep segment tree uh, the same way I described earlier, that is, we for each line there is like a maximum of the column. I think this can lead to an actually good solution, but it will be in n log squared, and it will be awkward to do so, especially in our case. And this will get 100 points, don't worry. So what I want to do is micro optimize because there's a solution in nlog. The issue is that if we sweep line and we try to keep for each position some information on the column, then it's kind of weird because at this point in time, so unless we do something extra, and I don't really like that thing, uh, like you can't just keep the max. Clearly, you can't just keep the maximum on the column because then you have the maximum of these values as well, which should not be included in the query that you want for this value, for this point. So, if I remember, there's like some weird stack thing that you do for some reason, and clearly you'll keep more points along each column, but you'll only keep like the maximum prefix or something. Those that yeah, those that are maximum prefixes or something like that, or suffix. So sweeping by this specific line is pretty weird again because we won't have the actual information that we want. So then I ask you this: what is so far? What we've done is we've taken this line, this horizontal line, and we said we are moving it upwards. So then we are sweeping it like line by line. We are going. We are basically sweeping the line across the figure. What would be another line? So like literally any line in the 2D plane that would work better for our drawing. So for that, I want to leave uh, 1 minute. You can come here on drawing new drawing number 4 and draw a support line that, although we don't know what it would do or how to do it, it would work better for our house. So not horizontal line. Okay. So here, but where to? Mm, wait, so I think you mean that we should sweep line the vertical axis, no? It looks like because you describe this as ranges, at least horizontally, on the vertical side, no? Am I understanding correctly? I'm sorry if they make you like log in uh, to come over here. But again, I'm not sure if uh, wait, if sweeping by vertical axis is preferable, sort of almost for the same reasons as before, because if we are to describe, so basically we might say that I deduce, at least from this drawing, that this box we can solve very easily, and then we might do something special that is that takes into account the indices better for the triangle. But two issues with the triangle, if we are to sweep by the vertical axis, is first of all, like we are not only bound by a weird thing over here, like because the axis would be here and we have to start the query later, but also because we have to end it at some earlier point. Whereas when we sweep lined the horizontal axis, we had at least, although it was awkward how to manage the empty space between the actual axis and where the query is supposed to start, we at least could take like the maximum on a prefix. But in such a case, we have to take the maximum on a range that is sort of variable, although d is constant, but it's still variable. And again, it might lead to a solution, but it isn't immediately obvious, at least to me, how we could do so. Uh, so in this case, um, we might see that although unsatisfactorily so, we discussed how what the horizontal line would look like, what a sweep line with a horizontal line would look like, on the vertical line would look like. But if you notice, there are a total of five lines in a house. There is this diagonal line, there is this other diagonal line, well, there is just the vertical line and then the horizontal line. And we fixed two of them. So how about we fix one of these for change? So let's sweep line, whatever that means, by the diagonal axis. And maybe you come to appreciate it right now, but it's technically a bit better because at least right now, uh, before we had two sides, for example, that were awkward. There was like the left side because there was the empty side on the left side, and there was the empty side, empty stuff on the right side. That was awkward. But now, if we look at uh, now we have a, an entire line segment from the query that is common with the sweep axis in our case, which is really great because it means that we could do prefix stuff from here if we were to find a prefix. Okay. Most notably, I think you might have seen this when it comes to do sweep lines on like tilted squares. So you have to maybe get the sum or hopefully not the maximum over rectangular regions such as this one. This is when they give you something like xj minus xi plus yj minus yi is less than d. For a fixed xi and yi, the range of xj, yj looks like this. And in such cases, maybe you know to like um, rotate the plane. So when we rotate a plane, and what they tell us to do when we rotate a plane is to set, instead of the coordinates xi and yi, to give it the one of the diagonals, the diagonal indices, and then the other diagonal index. So we change the coordinates from xi yi to x minus I, xi plus yi. After we do this coordinate change, we will get instead that this looks like a rectangular region, a square region, in fact. But normally, then, if we were to sweep line in such a case with the horizontal axis over this newly changed coordinate system, then back in the normal plane, it would still look as though we are sweep lining this diagonal line, actually. I hope you can agree to that. Because if the transition from here to here was a rotation, then the transition from here to here will be another rotation, just the rotation backwards. Uh, yeah, I think I might be able to show you some code, but right now I don't actually have code because I'm not actually talking about code, unfortunately. Right now, what really happens is that at the core of it, we actually just to want to get a trivial query or break the house down into more such queries. And I've discussed that this particular case when we have like such a rectangular query where the fixed axis is over here and uh, we need to take the maximum from this fixed axis on this range of columns until the very bottom. This is the trivial query. And also, this is I need to mention this right now because otherwise later it will appear as a random thing. We can also do a query for fixed. So for we can do the following queries for a give fixed d, so like a constant d. We can get the maximum over every single square of range d, or any query for a square of range of size of length d. We can get the maximum with a sweep line. So then the question is, how do we break the house down into more or into multiple of these trivial queries, like without actually having to think too much. And I said a good first step is to fix the sweep line axis as this diagonal axis, which I've shown to you that if we were to solve this a problem looking like this with a fixed d, so tell the maximum on this square of length d, but it's a rhombus instead. It's like a rotated square. Then after rotating the plane and changing the coordinates from xi yi to xi minus yi with xi plus yi, so this will be the new x coordinate, this the new y coordinate, then it will change to basically this other trivial query, for instance, because we've rotated it to a thing, to a square thing. But essentially, in the original scenario, we were sweep lining by one of the diagonal axes. If in this case we are sweep lining by the horizontal axis, but after we've rotated, then before we rotated, we were sweep lining by diagonal axis. Yes, but very good idea. This is a very good idea, but it has an issue. Um, so you say we could update parallelly. Um, I think there might be an issue with that. So the problem is that um uh, if we are sweep lining by this axis right now, then indeed we can get this rectangular range. Very good. So all that it remains to do for our little house is to find a way to describe everything below it. And we can, like as you've shown here, we can find another shape that we can intersect this with. But the problem is the following. Um, when we said that we can, so maybe we can like build a 2D structure to range, to query range for this, I don't care. Like, yeah, maybe that is valid. But when we said that we are sweep lining, when we said that we are answering such a query by sweep line, so this your figure is technically wrong because it has to go all the way down, but whatever. When we said that we are sweep lining, we said that for each column we are going to keep the maximum on that row, basically. But if we are sweep lining by this axis, by this diagonal axis, then it means that maybe we want to query like a bunch of points on it. Like any point on it will be a valid uh, query. And for the first plane, this will be fine. But for the second query, for this one, for instance, which might look like this, the square region of the second plane will look like this. So if we are sweep lining again by this axis, then any query along this axis will be equally valid. We might expect to get it. So then when we get this query and we divide it with this rectangular region, when initially we had this rectangular region, notice that for the red region, we are querying these this set of columns to get the maximum for this entire thing. But in the second case, we are querying the same set of columns to get the maximum over only this set. And before we said that each position will have the maximum on the entire column, but this is not the maximum on the entire column. It depends on the query. Sort the updates by y-axis. Well, that is the issue. because if we sweep line, we only apply these two paradigms, then we assume that in the segment tree that we are going to keep, we are only keeping the maximum from that position downwards. So the second that we fix one of the axes, um, first of all, like we can't do first the blue thing and then the red thing because the DP cannot like uh, the issue in such a case if we first do the blue transitions and then we do the red transitions is that actually the transitions might look like event number one goes with a red transition to event number 17, which goes to event number 32 with a blue transition, and then event number 32 goes to event number 46 with a blue transition again, but then we have to do a red transition from 46 to 117 and so on. The problem is on finding the center. No, the issue is that, but it's very good intuition to break it like this, but it's incomplete. I mean, maybe it works, but you have to do a lot of juggling to get that, and uh, maybe y- uh, maybe you can, but it's like I'm not sure how. It might be really hard. So the second that we fix this axis, and we said that okay, now we can get any query of this. We can tolerate queries of this type. This is fine. But then the issue comes when we want to query this red box. The issue comes from two facts. One, when we query this box, it might also be the case that you've seen in a regular sweep line that when you are at some current line, you may get a query like this from any point on the current line and maybe a point later on the same line. So if this is the line that we are sweep lining, but okay, we are sweep lining upwards, so this goes upwards, then we might get a query from this point, which asks us to aggregate uh, this this rhombus, and then we also want to get this square. The issue is not in finding whatever is in the blue side, but what is in the orange side. Because notice, if we were to keep the same structure both for red and for orange, then what happens with these queries over here? Because orange wants from 23 to 110, um, the maximum on the columns, but bounded by this line. So from this line downwards. But red wants from 23 to 100 and also maybe to like 210 or over here, but doesn't matter. It wants the maximum on these columns, but from this line downwards. So the same structure cannot actually answer both of them unless we do something extra. So then we can't actually sweep line. Is that clear? So the problem is that the two shapes that we have, essentially at the bottom of it, the two shapes do not share an axis because we really only have like this. So the first one is a rhombus and the second one is a square. And notice how none of these lines match. Like one has only diagonal lines and the other only has like horizontal and vertical lines. They do not match. But if we were to break down the house into multiple shapes which all share an axis, and in our case it should be this horizontal axis, then it will be good. So we will define a shape right now as a parallelogram. I'm not sure how to write that. But a shape for us, essentially, what it needs to be is a range that is described by the bounding of two lines. So something like this, and in earlier in our case, okay. So let me make it. So a square is a shape, a parallelogram shape, because it's bounded by these two lines, and then later these two lines. So everything between the blue and the black. Okay, it should. I think this is enough for the last lesson. Yeah. I'd be stopping right now either way. It was just a matter of if showing a code that works for this is interesting for you. Yeah. So what would happen here is that, as I said, he divides the ranges into three parts, and if I'm not mistaken, this is a query for the like uh, rectangular region, uh, the square region. This is a query for the red region, the red shear. I think it's, yeah, I think it's called like shear region, which actually is a modification from XY to, I think, like X minus Y. Uh, no, X and X minus Y or something like that. And I think you can notice this because one of the fixed line that we are sweeping is this, and then the queries are done over variables of the form X. So he has from like left to right, from the left half point to the right to the current coordinate. He calls them norm because they need to be compressed because they give you like 10 to the 9. And the right shear region, which is this one, which he queries immediately because he delays the updates that are done to it, I think. Uh, but yeah, um, and we should sort by the difference between the coordinates, which is basically this line. Are there any questions that I can answer right now? Can you also explain the solution of day two problem A? Should I do this also? Uh, you think I can? So I assume day two is like very old day two. Like, wait, am I still? Okay, yeah. So for that, I'll be brief and then I'll have my closing statement just after. So for day two, it was said that uh, we need to sort a permutation and we can do a swap at any point. We can do like one random swap between two elements from I and J, and except for that, we need to do adjacent uh, swaps. And we are asked how many operations we need to do, given that we can choose our extra swap however we want. If we didn't have an extra swap, then the number of adjacent swaps is equal to number of inversions, count of inversions. So yeah. So the question is, what is the swap that we can do to minimize the count of inversions as much as possible? And first, we notice that the swap we should do it at the very beginning because otherwise, the elements that we swap we could have swapped at the beginning instead of swapping them later after multiple adjacent swaps. So we swap something at the beginning, I and j, and then we want to see how we affect the number of inversions for that matter. And if we are to plot uh, elements I, pi into the plane, then it looks like some random thing. I don't know. But then a swap between, like, let's say this element, which is like 5p5, and this element, which is 16p16. How many inversions will it clear? Well, first of all, one, clearly, because they are in an inversion. It never makes sense to not swap something that is already in an inversion, like something less to something greater. So this is I and this is pi. And also we notice that uh, initially, if we look at this sort of rectangle, all the points in here made one inversion with uh, p6, p16, and this element made one inversion with all the elements in the rectangle. So after we swap them, we will get minus 2 times the number of points in the rectangle. And because of this, then it makes sense to expand the rectangle as much as possible, which we later see that it means that we should, like, the left hand point of the swap that we should do should be on the maximum on prefixes, and the right element should uh, be on minimum on prefix. So this is in on suffix. Sorry. Then for a point, how we will now try to ask what would be the swaps, because we've said that all the swaps that make sense will have one left hand point over here, like one of these elements, and one right hand point over here. So then we look and check what is the set of swaps that make sense for this. And it turns out that any right hand point from this set with any left hand point from this set will have this point in the aforementioned uh, submatrix, which counts to the number of inversions that we get reduced by. So then we can sort of say that this is an axis, this is another axis, uh, and then for all points x, y with uh, L1 less than x less than R1 and L2 less than y less than R2. Well, L2 and R2 are these two values, and this is L1 and R1. We, for all of these points, we add plus 2, and we want the point with the maximum value. So because this is a sub matrix plus 2, we can do sweep line. I can't cover that in detail, but I hope that's a better overview. No questions? No, okay. Yeah, sorry, I did not see that. Okay, so to close things off, because we won't see each other for a long time, probably. Uh, yeah, I'd just like to say that it was nice working with you. I hope it was also nice for you to be working with me. I hope you like the problems and so on, and the topics for that matter. And if even furthermore, oh yeah, sorry. If even in the future, like, I'd still try to send homeworks in the off time, but maybe not at the frequency that I've done in these past few days. But at any point, if you have any problems that you maybe don't know how to solve and you can find a solution, and you want some help, you know my Discord handle. If you ever need advice, you can text me and we can discuss. So don't be afraid to message me for whatever help you might need in the future. So yeah, thanks a lot, guys. Wait, I can't actually, right? Uh, yeah, and yeah, I'll see you sometime in the future, probably. Goodbye.